This time what we're going to do is we're going to throw up another object straight in the air. We'll take some type of baseball. Our ball is going to be thrown up, which means it has some velocity initial, we'll say 20 meters per second. We want to answer the questions: how high up will it go? How long will it be in the air? Draw the path of the ball. So the ball reaches up here to some maximum height. We can call this y at the top. And then there's t to the top. And we know that v at the top equals 0. And then when the ball reaches the top, it's going to turn around and come back down. Now, the best approach is to put the origin where we throw the ball. So this becomes y initial equals 0 meters. And then whatever we go above us is y at the top. That's our maximum height. We can call that y top or y max. That's as high up as it'll go, and then it'll return back to y initial. This is kind of like the picture we have where we've put in everything we know. Of course, this v at the top equals 0. That's our bonus piece of information that wouldn't be given to us in the wording of the problem, because this is assumed that we know that when something comes up, it reaches it momentarily stops at the top and then comes back down. The other thing that they won't come out and initially tell you is that your gravity is 9.8 meters per second squared down. That's assumed that you'll assume that that's the Earth's gravity, and that's what it would be if you weren't explicitly told that. So, one thing that we want to look at is our velocity versus time graph, so we can kind of see what's going on. So the ball leaves our hand with some positive velocity, 20 meters per second. And then what happens is the ball then slows down, reaches 0, this is when it's at the top, and then it continues to, then it re-accelerates towards the Earth. Let's see what happens. We can get this by thinking about the fact that v final is v initial plus a delta t. So if we're thinking about v final being our velocity at some point in time after it leaves our hand, this is what we see. We see 20 meters per second minus 9.8 delta t. So as time gets larger, this becomes, so after 1 second, you'd have 20 minus 9.8, which means this would be something close to 10.2. And so as the ball's going up, it's slowing down. There'll come a point where this t times 9.8 will equal 20. And that's right here when it comes to a stop at the top. Then for times larger than that, this number is a larger negative number than 20, and the ball is starting to get a negative velocity, and it's coming back down to the ground. And this is exactly what our velocity versus time graph shows. And we can actually think about what's going on in our position, because we see that as we reach here, we have what? The area underneath this curve is a maximum positive value. Then we build in a negative value, and these two areas would cancel, so that the end, at this time when it comes back to our hand, we have displaced no distance, because we have the positive and negative areas adding up to be 0. So this graph gives us a lot of good information about what's going on with the ball. It leaves our hand, it slows down, reaches 0, then reaches a maximum back down here of negative 20 when it reaches our hand again. When we're looking at this, we know that the slope of a velocity versus time graph is delta v over delta t. And in this case, this slope is pointing downward, and it's a negative 9.8 meters per second squared, because it's the gravity. And so this is a really nice graph to look at to understand what the motion of this ball is. All right, so let's get back to our question at hand about what we're going to be trying to solve. And we're going to try to look at this a little bit differently. So let's actually do this. Let's start with, how long will the ball be in the air? Well, we can actually use this. X final minus x initial is equal to vi delta t plus 1/2 a delta t squared. And here's something that's kind of interesting to think about. The ball starts where? At x initial, which is 0. If the ball comes back to my hand, it's at x final. Its final spot is back in my hand at 0. And this has to be 20 times our delta t minus 1/2 of the 9.8 times delta t squared. So what we see is that 0 is, I'm going to call this t just to save the one, 20 minus 4.9 t squared. We have two possible things. We can factor out a t, and we have 20 minus 4.9 t equals 0. So one of the solutions is that t equals 0. That's an immediate solution. If we plugged in t equals 0, we would see that 0 times everything is 0. And that's one of the solutions. That's when the ball is in my hand before it leaves. So this is what we call it's a solution, but it's not the one we're looking for. What we want to do is we want to solve inside of here for that time when the ball comes back to my hand. And so what you can do is you can solve this and set this equal to 0 because it's another solution. And so what we see that t is equal to negative 20 divided by 4.9. We get that should be 4.08 seconds. Now let's check to see if this is a good solution. Let's check this by looking at how long does it take to get to the top. So how long does it take to get to the top? We know that v final is v initial plus a delta t, and at the top it's 0. So 0 is equal to 20 minus 9.8 delta t. And so we see that delta t is negative 20 over negative 9.8. And so this is delta t to the top. And delta t to the top is going to be 2.04 seconds. And so we know that the time up is equal to the time down because gravity works equally up and down on it. And so the total time then is 4.08 seconds. So our solution here is a good solution to our problem. All right? So this was just another way to think about using that equation where in this case, it should have been y final minus y initial is equal to v initial delta t plus 1/2 at squared. That was another way to think about this equation. Tells us properties of our ball's location, our object's location, based on final and initial positions. Even if it returns back to the original spot, there'll be a time. We saw that the solution actually had the two times. It had when it was in our hand initially at t equals 0, and some later time it crossed that spot again. And this equation gave us those solutions without having to do some other things. So these equations are really powerful in terms of telling us an object's location, describing how it's going to move. And that's why these solutions for motion are so valuable, because they enable us to predict where things will be. So this is just another example. And we still need to get how high to the top. And we can get that because we can get that with either, now with this equation, because we have the t, so we know that y top minus 0 is equal to 20 times our 2.04 minus 1/2 of 9.8 times 2.04 squared. So y to the top should be equal to, and y top is 20.4. So this ball will go up 20.4 meters before hitting its velocity of 0 at the top before it comes back down to the ground. So we looked at a different method of getting the final time down, how long will it be in the air, just by solving the fact that it was at that same position at both times, and we found how high up it went and how long it took to get to the top. And we looked at how our velocity versus time graph would look for this type of motion when we throw something up in the air.